like a little bit of this checking here. It looks right?
Yeah. You just, I'm sorry, what did you do?
I'll just multiply this onto these three, and multiply this onto these three, and then combine them together.
Yeah.
You get one large polynomial, okay, in standard form. Now you can take the derivative of this. You know f prime, right? F prime, no big deal. Use your power rules and the sum rules and all that jazz. You have 3x squared minus 4x minus 1. We know that is the answer to the derivative of this problem. Okay, we would like to bypass such things as having to multiply out every single polynomial on the face of the planet before we can take the derivative. So we're going to come up with a rule that will allow us to take the derivative of a product without expanding it first. Okay, that's the idea. And so too for quotients. The rule, without proving it to you, since you look
I have a question.
sleepy enough anyway. Yeah.
Where did you get f prime from?
I just compute it very quickly. I know you bring down the 3 and make that a 2. Right? This power rule. I'm just doing a power rule.
Oh, I forgot. Okay.
Yeah.
So just like 20 minutes ago.
Yeah, I hear. I hear. But you're busy trying to scare me out there, so that probably threw you off a little bit too. Right. So. All right. Yeah. So the rule for a product is, if you want to take the derivative when you have a product of two functions, I'm going to write the notation like this: d dx. d dx, the derivative of a product of two functions. The rule is the first times the derivative of the second plus the second times the derivative of the first. Okay. So that would be the rule. Watch out, I'm falling over. That would be the rule using the d dx notation. It's better to memorize what I said though. First times derivative of the second plus second times derivative of the first. And should you invert these two terms, it will not matter at all because you are summing them together. So you could easily say, right, the second times derivative of the first plus the first times derivative of the second, that won't alter anything at all. Not only that, if you were to switch these two, right here, and you said the derivative of the second times the first, well, it's a product, so it doesn't matter. So as long as you get each function coupled with the derivative of the other one, and you add that together, you have your derivative, okay? The formula is very flexible in that sense. Lee, that make good sense? Flexibility of the formula?
Thank you.
So let's take this derivative again, without multiplying it all out, alleviating that burden. Take the derivative of this. So it looks like the first function is the quadratic one, and the second one I would consider to be the linear one. So one takes the derivative now, df dx, bring up good markers here, will be, if I take the first, x squared minus 3x plus 2, right? There's the first function over there, times the derivative of the second. What's the derivative of the second function?
1.
1 times 1. That's the derivative of the second function. Plus the second function, which is x plus 1, times the derivative of the first.
2x minus 3.
Good. 2x minus 3. There's our answer. There's our derivative of the exact same function. Which means if we multiplied this out and added it together, we would get the exact same quadratic down there. And I'm sure we will. We're going to do it, right? So this times 1 is itself. Plus, if I multiply this out now, we'll have 2x squared plus 2x minus 3x minus 3. If I now combine like terms, I'll have a 3x squared. This and this are the same. So 3x squared, negative 3x, and this one, right? Going to give us a negative 4x, which is negative 4x. And plus 2 minus 3 is negative 1. They are the same thing, of course. Okay? Now, in most cases, it will not be necessary to multiply out this side and add them together. Right? So you may have thought for a second, over there, what did I do first? I multiplied everything out and took the derivative. Over here, I took the derivative and multiplied everything out, so it doesn't seem that much quicker. Right? But in general, you will not be multiplying it out after this stage. Right? Not really that necessary. You may want to compare the back of the book sometimes to make sure you have the right answer, but in general, it's not that necessary. And it may be a disadvantage in some cases. All right, you guys got the quotient? Sorry, product rule okay? Yeah. You want to do one more of the product real quick? One more. I'll take one from the textbook this time. Oh, next time is trig.
Well, isn't this like what we just
No.
did before?
But before with a new rule. I'm giving you a new rule. How?
Oh, because you're multiplying it, it means that you're adding it.
If I multiply two functions, I can take the derivative of the whole thing without having to change it first. Right? First times the derivative of the second, plus second times the derivative of the first. Special rule for products. Special rule for when I times two functions together. So number 12 in the text, number 11 in the textbook has the function. I'm going to use x's as they have w's for no good stinking reason. So I'm going to use x's. G of x is e to the x. I'm going to bring that one back again. And times x cubed minus 1. All right, there's our function. I want to take its derivative. That is, I want to find the slope of this curve anywhere. So dg dx going to be. I see this as a product of two functions, right? The first one is e to the x, and the second one is x cubed minus 1. So is the first times the derivative of the second. What's the derivative of the second? 3x squared. And this is faster if you just think like that on your feet. It's faster than writing the full notation. I could write d dx of x cubed minus 1 here in parentheses, but it's going to be easy to facilitate if you just like look at it and just knock it right in there. Plus the second x cubed minus 1 times the derivative of the first. So it's e to the x back again, right? E to the x. Okay. There's the derivative of that product. Now in this case, anytime you see, granted, this is the slope of this curve anywhere, but for the vast majority of problems you're going to do later, you're going to be setting things equal to 0, you're going to be setting things equal to other things, and you're going to want to be able to factor and solve these things equal to some number, usually 0. So it behooves you now to start getting used to the algebra, and anytime you see a common factor here, like the e to the x, factor it off and simplify your result. Okay? Factor it off. So to complete this, make it look as pretty as possible, we take the e to the x out of both of these. We'll be left with 3x squared plus x cubed minus 1. And I would even write it in standard form, the highest power first, e to the x times x cubed plus 3x squared minus 1. There's your derivative in its most pristine form. Okay? Factored form is what you want, whenever possible. Okay? Because you're going to be doing a lot of factoring in this class. You got to set equal to 0. Because a second ago, just for example, if they had said, where is this have a horizontal tangent, then I would set this equal to 0. That would have been my problem, like I did a minute ago. And so that means, what do I do now? I don't know. How am I going to do this junk? But down here, if I said this equals 0, it's pretty clear what to do. Either e to the x is 0, or this polynomial is 0, and now I know what I have to work with. I have to work with this polynomial set equal to 0, if I had that case. That's horizontal tangents. Okay? All right, so that was another product rule. Now we'll do a quotient rule. Let me first write it. Its formula is a bit more extensive than this one, but not that bad. The derivative of a quotient of two functions, so this one has a top and a bottom, instead of the first and the second, is going to be the bottom times the derivative of the top minus, as opposed to a plus. So when you have a product rule, you have a product, it becomes a plus for the derivative in the formula. You have a quotient, it becomes minus.